Hello, welcome to our last video in our series on portfolio theory. Now what we're going to talk about now is the market portfolio and the CAPM. Now our roadmap will be that we'll start considering portfolios of many risky assets, not just two as we have done so far, and by doing that we'll be able to derive a particularly interesting efficient frontier and a tangency portfolio. Now this will set the platform that we can use then to jump into the capital allocation pricing model, which maybe you haven't heard of so far, but if you continue in the sequence of finance in your studies, you will be using it a lot of times. Now within CAPM we're going to focus in particular in two things. CAPM will give us a proper measure of risk, and also it will give us a pricing equation. That is, it will tell us how we should find the proper compensation for holding risk. So let's start with the argument that is going to lead us to derivation of an efficient frontier when we consider every possible asset in the economy. So suppose that we have, instead of two risky assets, we have three risky assets. And we go ahead and we plot them again, as usual, in a graph that has in its vertical axis the expected return of a portfolio of such three risky assets and the standard deviation. So let's call them 1, 2, and 3, these risky assets, and their associated pairs of expected return and standard deviation. Suppose that they sit on those points, labeled accordingly. Now, when we have three risky assets, one straightforward thing that we can do is that we can think about building portfolios of only two of them. For example, we could think about building portfolios of 1 and 2, and then, as we know, we would get something that looks like that. Of course, the particular bending of the curve will depend on the actual correlation between the two. We would also consider building portfolios of 1 and 3, and we can also consider building portfolios of 2 and 3. Now, but of course, we could also consider building portfolios of portfolios. That is, for example, we could consider building a portfolio of we could consider building a portfolio of that portfolio of 2 and 3 and 1, and then building all possibilities that we have there and obtaining a curve like that. Of course, we can replicate this argument for every possible portfolio of two of these risky assets that we can imagine. That is, in reality, we can, in essence, we can create any possible portfolio of three risky assets by replicating those arguments all along. Of course, we can also consider short sell positions in each one of these three assets. Now, once we have done all of that and we have plotted the particular points of expected return and standard deviation that we obtain when one continues that procedure, then we're going to find out that if we choose the lowest standard deviation for a given expected return out of all these mixes that we have done, all of these are going to plot in a curve like that. A curve that looks like the type of curve that we have been obtaining too itself. And it has also a portfolio which has the lowest variance of all, and it also divides the curve into an efficient part and an inefficient part. That would be the efficient part. But we can continue throwing more and more in, but of course, we can also consider throwing a risk-free asset into the mix and creating a tangency portfolio. And that straight line, when we have three only assets, will give us the efficient frontier of the two risky assets and the risk-free asset. and it will have, of course, its tangency portfolio. But now we can continue adding risky assets to the mix. We can consider another risky asset, another one, another one, another one that we find out there, another one, another one, and another one, and another one. And then we can continue replicating this argument, building portfolios of 2 assets only, building every single portfolio that we can imagine, and we will expect that now, when we have thrown more risky assets, by following the same procedure, we can find, at least we can think of it graphically, a new efficient frontier, which is going to be to the left of the previous one. That is, it's going to be in a position that will turn out to be more attractive because we have more risky assets now to build portfolios with. Of course, we can also consider, with that efficient frontier of risky assets only, we can also consider the risk-free asset, find the tangency portfolio and its associated capital allocation line. That one will be then, given this many risky assets, that last straight line will be the efficient frontier. Anything below that will be inefficient. Now, we could continue throwing more and more risky assets. And we could presumably expect further moves in direction northwest with associated capital allocation lines and tangency portfolios that will give us somehow better deals and an efficient frontier that sits further northwest. But how long can we continue doing this? Unfortunately, the sky is not the limit here. It is market risk that sets the limit here. Once we have eliminated all firm-specific risk, we will not obtain any further diversification gains translated into further moves to the direction northwest of the efficient frontier. We are stuck with market risk, and that is something we cannot diversify away by incorporating even more stocks into the mix. So at this point, we have reached the efficient frontier of all assets in the economy, even if we haven't used all of them. As long as we have eliminated all firm-specific risk, we would presumably reach all the expanding possibilities that we can obtain and push the efficient frontier further northwest as much as possible. Now, this capital allocation line of this final tangency portfolio is the one that one obtains when all risky assets have been included. The tangency portfolio obtained this way is potentially a portfolio of all single assets in the economy. But also, it has the maximum Sharpe ratio that we can obtain with all the risky assets available. And also importantly, it has no market risk. Now, given this, it is probably clear to you that such portfolio is the one that all rational investors would like to choose and combine it with a risk-free asset. That is, all rational investors will sit, their actual choice will sit on the capital allocation line of the tangency portfolio, of this tangency portfolio. Now, once we have established this, we are in a position to somehow bring back our issue, our question, which we left unanswered in a previous video about building a proper measure of risk. And this is an answer that the capital asset pricing model gives. Now, for the capital asset pricing model, this tendency portfolio is crucial. And CAPM refers to it as the market portfolio. Now, since it's the portfolio that in principle is formed with all risky assets in the economy, and also is the one that is going to be preferred by every investor, by every rational investor, and it will be combined with a risk-free asset. Now, one can look at it as a reasonable tool to define a proper measure of risk. Since it only contains market risk, it makes sense that finding commitment with the return of this particular portfolio will give us an idea of how much market risk a given return contains. And if you remember from that video, the one on risk and return, what really matters is market risk. The actual compensation for risk should only depend on the amount of market risk that a given risky asset has. Any firm-specific risk is irrelevant. So it is fundamental that we find a tool to capture, to be able to establish the amount of market risk that a given portfolio or risky asset has. Now, CAPM just reasons that, okay, the source of market risk is perfectly specified by the return of this market portfolio. In other words, this is nothing but saying what I just said before. It is commitment with the return of the market portfolio, what it will be used in order to find how much market risk a given risky asset has. The capital allocation line of this portfolio of all risky assets, which has no market risk whatsoever, and whose Sharpe ratio is the highest that it can be obtained by building portfolios of all the risky assets in the economy, is also known as the capital market line. So we can imagine that when we consider every single risky asset, we will end up, when we do the typical graph that we have been doing, we'll end up with a particular efficient frontier of all risky assets, the one depicted there with a red line, and the efficient frontier when we also add to it the risk-free asset. And since this capital allocation line, this capital market line, according to CAPM, is the one that gives that every rational investor will pick. Oh, I got lost here. Sorry. So this is the capital market line. And since the tendency portfolio, according to CAPM, is this market portfolio, the portfolio built with all assets in the economy and the portfolio that has the largest Sharpe ratio, we label that tendency portfolio with an M for market portfolio. What we're going to now say is, okay, so we have a tool to capture market risk. How are we going to use this tool to compute the amount of market risk that a given portfolio has, or a given individual financial asset? Now, suppose that we have an individual financial asset, an individual stock. Let's call it stock I. Now, the measure that quantifies the market risk of an individual stock is what CAPM calls the beta of the asset. And it's defined in the following way. It's the ratio, the covariance of the return of asset I with the market portfolio and divided by the variance of the market, of the return of the market portfolio. Now, in order to interpret this ratio, it will be interesting to express the covariance in terms of the correlation that we have done before. So the covariance, using its definition, can be written in terms of the correlation as the product of the two standard deviations times the correlation of the return of this asset I with the return of the market portfolio, divided once again by the variance of the return of the market portfolio. Now, some cancellations happen there, and we end up with that expression. Now, let's focus on the first term of that product in that expression. That is the ratio of the standard deviation of the return of the standard deviation of the return of this individual asset or stock divided by the standard deviation of the return of the market portfolio. Somehow it gives us an idea of total risk, including firm-specific risk, to the market risk of the of market risk measured by the standard deviation of the return of the market portfolio. Now, however, since some of that market risk is not however, since that proportion, that ratio that gives somehow the total risk of the asset is a fraction of the market risk measured as the standard deviation of the return of the market portfolio. Since this fraction has a part that contains firm-specific risk, we need to do something with it. It's not all of our interest, and then we weight it, we multiply it by the particular correlation between the return of the stock and the return of the market portfolio. Somehow we weight it by how much the two assets co-move together. And recall that the value of this correlation is a value between -1 and 1. So if there is firm-specific risk, this correlation will be somewhere between -1 and 1. And therefore, it will reduce when multiplied by this fraction, it will reduce the value of the ratio of the two standard deviations. For example, we can continue interpreting this and, for example, consider the case where the correlation, the extreme case where the correlation is equal to 1. And suppose that the ratio of the two standard deviations is actually equal to 1 too. What happens here? Well, all risk in the return of asset I, since the correlation with the market is 1, will be market risk. And on top of that, the amount of this market risk is exactly equal to the market risk of the return of the market portfolio. It does make sense to expect that the compensation for risk of this individual return should be equal to the compensation for risk that we obtain, that it is given to the return of the market portfolio. Now, we can suppose instead that the correlation between those two assets, the asset I and the market portfolio, is actually equal to 0. When would this happen? This would happen in a situation where there is no market risk whatsoever. All risk in asset I is firm-specific. And as we reasoned in our video on risk and return, firm-specific doesn't matter. And firm-specific should not be rewarded, should not be compensated. Which means that if all risk is firm-specific risk, the respective return of this stock should be exactly equal to the risk-free rate, or rather, the risk premium of the return, the risk premium of this stock should be exactly equal to 0. We could also suppose that if, for example, the correlation happens to be less than 0, this implies that this asset is a good tool to hedge. If we think about the return of market portfolios capturing market risk, then the return of the market portfolio is also telling us when we are in good times and when we are in bad times. Times of good returns will be times of good times in the economy. Times of bad returns of the market portfolio would be times of bad times. Now, if the correlation, if the co-movement, if these two returns move in opposite ways, we can use asset I to actually hedge, to somehow boost our returns exactly at the point when we most need them. This possibility of hedging that this asset has then when the correlation is less than 0, should imply that the risk premium of this asset should actually be lower than 0. That is, we're not going to be compensated. Not only we're not going to get an expected return in excess of the risk-free rate, higher than the risk-free rate, we're actually going to get less than that, because we can use this return to do hedging. Now, if we put all these reflections together, we can start to understand how we can create, how CAPM establishes the proper compensation for risk given a value of the quantity of risk embedded in a given asset. That is, giving a value of beta. And this way of fixing that compensation for risk is embedded in what is known as the pricing equation of CAPM. So CAPM then tells us that the return of an asset I should have as risk premium the one given by that expression. It should be, the risk premium of an asset I should be equal to the quantity of risk measured by beta times the price of that risk measured by the risk premium of the return of the market portfolio. Now, this equation is actually a straight line and is known as, when illustrated graphically, is known as the security market line. Let's look at it. We can write it in this fashion. We can just move the risk-free rate to the right-hand side, and we can see then why this actually is a straight line if we plot it in a graph that has on its vertical line the expected return and on its horizontal line the particular quantity of risk measured by beta. We can bring back again the equation of a straight line that we probably remember from high school mathematics. And then we can see that if we do that, we can look at this equation as given our y's equal to the expected returns, our x's would be the betas, our a, that is the intercept, will be then the risk-free rate, and our slope, the b, will be the risk premium of the return of the market portfolio. So if we go ahead and we plot this equation in a graph, in this case, the vertical axis will have the expected return, and now the horizontal axis will have not the standard deviation but the beta, we will see that we should find, when plotting this line, a straight line, this equation, a straight line. Now, since we have established somehow analytically that this should be a straight line, we know that to plot it, once again, all we need is to find 2 points that sit on that line. One natural one would be, for example, the one that we obtain by setting beta equal to 1. Or sorry, the one that we obtain by setting beta equal to 0. When we do that, the expected return is equal to the risk-free rate. Another point that we know is going to sit on that line is, for example, the one that we obtain when we set beta equal to 1. In that case, the equation tells us this straight line, the equation of this straight line, the pricing equation of CAPM, tells us that the expected return should be equal. If we plug a value of 1 into the beta, we obtain an expected return equal to the expected return of the market portfolio. So we obtain that point there. Again, we draw a straight line through those 2 points, and we obtain the graphical illustration of the pricing equation of the capital asset pricing model. Now, we're going to finish with one last comment. Everything we have said in this video is actually quite theoretical. And we have been talking about this portfolio of all assets in the economy, which has the property that it has the highest Sharpe ratio of all, that it sits, that is also plays the role of this tangency portfolio of the fishing frontier when we consider every single asset in the economy, and thus it is the portfolio that any rational investor would theoretically want to invest in. Of course, everything in this somehow theoretical derivation sounds good, with one exception. We don't know what the market portfolio, we do not observe the market portfolio. What is the market portfolio? I mean, okay, it's something that is made a mix of every single risky asset in the economy, but that sounds like something that is difficult to create. And the answer is, yes, it is true. This, I mean, it is in real life, the market portfolio is not observable. So, in order to apply all these theoretical tools, in order to actually fully exploit the punchlines of CAPM, what we do is that we use as a proxy, as a representation, as something that could, empirically, somehow be close to this theoretical construction called the market portfolio, we use a general stock market index. For example, if we were in Sweden and we were just looking at local Swedish assets, a good choice would be OMX index, and the return of the market portfolio then would be represented by the return of this index. Okay, and this closes this sequence on portfolio theory.